Hi, and welcome to this new geometry gem where what I'm going to show you today is how to take a polyline and write a smoothing algorithm that is going to create a smooth curve that is going to be touching this polyline over several iterations. So for example, if I have iteration 0, it's just the polyline. First iteration is like a it's not very refined polyline, but as I keep increasing my iterations, you can see how the smoothing definition is much nicer, and now it's basically a smooth curve. I'm going to show you how to make this curve closed, and I'm also going to show you an alternative to working a little bit with how these polyline smooths and snaps to the original contour polygon. This works in three-dimensional space, and it's a really easy algorithm to implement. And and nicely, it also happens that every one of these segments between every one of these curves between the control points corresponds to a quadratic B-spline. If you're interested in why that's important and what that means. So I'm going to be implementing this in Rhino and Grasshopper, which is an algorithmic modeling environment. But I'm going to be writing all the code in C#, and I'm going to be using no libraries or no geometry kernels. So if you're interested in this, you will see how learning from this example will make it very easy to translate this algorithm into any other programming language that you may be working with. I'm just using this here for the sake of visualization. It gives me a very nice interface to see this geometry. Okay, so I'm going to talk a little bit about the history of the algorithm and how I was inspired to do this gem, because I actually met the son of the creator of this algorithm very recently. And I'll talk a little bit about the history, and then I will explain how the algorithm works, and I will show an implementation of it. So buckle up, because it's going to be a lot of fun and super interesting. Okay, let's start with a little bit of history. I'm a professor, so I like not just writing algorithms, but talking about the history of what those algorithms. So this algorithm is pretty interesting because it was invented by George Chaikin in 1974, and we have to think that in the 70s, computer science and especially computer graphics was still very much in its infancy, and computers had very limited resources to drawing things on a screen. So coming up with algorithms to design or to display things such as smooth curvature, um, as opposed to just polylines, was actually something that a lot of people were working in. And doing it in an optimized, fast way in a computer that didn't have many resources, that was something very important back in the times. Right now, in 2020, we give all those things for granted because our computers are just like 3D, blah, 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 whatever. But back in the time, it's like 50 years ago, um, it was actually quite a big deal. So this algorithm was very interesting because from something as simple as a controlled polygon, so for example, just 4 points, it was able to generate something that felt like a smooth curvature. It's not exactly a smooth curvature because at the end of the day, in computer graphics, everything, circles, curves, any Bezier curves, sine curves, whatever, at the end of the day, is just a discretization of that into small pixels. But if you do it fine enough, then for the human eye, it looks like a smooth curvature, right? So this is what the algorithm is about taking a sequence of points, so for example, these 4 points or more, and coming up with a way of discretizing that in smaller segments, so many that it feels like it's a smooth curvature, all right? For example, like the way we're seeing here for 1, 2, 3, 4, and 5 control points, okay? And the idea is that this algorithm was really simple, and it came up with a very nice and elegant and fast way of doing this. And that's why it was very popular at the beginning in the 70s. And actually, there was another paper the year after, also published in the same journal, that proved that this algorithm was actually a way of creating a piecewise B-spline quadratic curve, which means that I'm not sure if I should get into that, but basically concatenating continuously a bunch of quadratic B-splines. which is what this algorithm, the result that it gives you. If you do some Googling, there are some papers out there that talk about the algorithm, and this one is, for example, is very helpful because it gives us a very nice description of how the algorithm works, and I'm going to explain this with a sketch in a second. But also, if you just do some Googling, there are a bunch of other, there are a bunch of like online places where you can see like how to write this algorithm, etc., etc. One of the most interesting ones is the one that Paul Chaikin, his son, the one that he wrote on his own website, right? And here you can choose to move the points around, and you can choose like levels of discretization. So, and I will also explain why this is. You see, 0 iterations, it's a polygon. 1 iteration, it starts to be a curve, but it's not quite there yet. 2 iterations, it looks smoother. 3, 4, and at some point, there are so many iterations that it actually does look smooth. But remember, it's just like tiny, tiny line segments one after the other. I will explain this in a second. And I also want to highlight this link. This is by Jim Juan. He's one of our followers, part of the community here at Parametric Camp. For this video, I issued a challenge in my live stream, and participants in the live stream were given 1 or 2 weeks, I forget, to try the algorithm themselves. And Jim actually wrote a full blog post about writing the algorithm, his findings, and how he did that. On his website, and the hurdles and the problems that he found. He couldn't include the endpoints, and he still wasn't able to figure out the closed polyline situation. So this was really interesting, and I encourage you to check this out. And if you want to learn more or alternative ways of doing that, but I'm going to try my own way on this video, on this gem, okay? And what I'm going to do is, in order to start that, I'm actually going to explain how the algorithm works. So let's do some sketching on the whiteboard. All right, so let's talk about the algorithm. And I actually love this algorithm because it's so easy and so straightforward to implement. Yet the result is so nice but you're gonna see like very soon. So let's start by imagining that we have a series of ordered points. So point number 1, 2, 3, 4, whatever, which we could use to draw a polyline along them. We don't really need the polyline for the reasons that I will explain, but it's all about thinking of those points and conceiving them as the control polygon that is going to drive this curve. The next step to the algorithm, this is an iterative algorithm. So what we do is we perform a smoothing operation on this control polygon many, many times. However many times depends on us. So the choice that we want of how smooth or how refined we want that curve. But the process is as follows. We go through iterations of smoothing this control polygon by doing the following. For each one of the segments, so for each one between 2 points, what we do is we find points. We find 2 points between any series of 2 control polygons, not control polygons, 2 of those points in the control polygon, with the rule that those points must be at a fourth of the starting point and a fourth of the end point. So you can see this point here is at a quarter of the relative distance to this point, and this other point is a quarter of the relative distance to this other point. This one is a quarter into this line, this one is a quarter before the end of the line, this one is a quarter, etc., etc. So you see where I'm going with this, right? And then as you have subdivided those you have created new points for a new control polygon, so you can join those points with a polygon, and then you get the first iteration of a smoother polygon than the one you started with. If you do this iteratively, so now if we take this control polygon and then we do the same thing, we find in between every pair of points, we find these new control points, so at a quarter distance from the ends, and then we join them again, you can see that the result is like yet a smoother curve than the one we started with. And if I repeat that process again, for example, you can see that I find a lot of points at a quarter of the endpoints. And if I join those again, then you can see that I end up with a much smoother curvature here. So this, as I said, we did this just for 3 iterations, and the curve actually looks pretty smooth already. So if you go all the way up to, for example, 6 iterations, then it's very difficult for the human eye to just to distinguish like the tiniest length segments. But this is the core of what we're going to be doing, just basically finding for an original set of points. We're going to be finding for each pair of points, we're going to be finding 2 points in between them at a quarter of the relative length of the curve, and we're going to use those new points to create a new control polygon like this. And we're going to do that iteratively, over and over, a control amount of times. I think a good rule of thumb is about 6 times to create like nice smooth curvature. But this is the core of the algorithm. You can see it's very, very simple. The only thing that we will need is to know how to calculate a point at a relative length between 2 points. So a point at 0.25 and another point at 0.75 in between these 2 points, and to do that iteratively. And for this, for the calculation of the line of the points between 2 lines, between 2 points, I already have a geometry gem that we did last week. I think it's number 6 or so, but you can look it up on the channel and it will pop up. Probably it will be on the link here in the description, or it will pop up somewhere as a card. All right. So it's just as simple as this. So how about we give it a try to implementing it? Okay, let's prepare our file. So what I'm going to do is, I'm here in Rhino, and what I would like to do is I would like to put here like a bunch of points. So I'm clicking on point, and I'm clicking left mouse to create a point and right mouse to repeat that action. All right. And I want to have the points here in Rhino because I will want to like drag them and move them to prove how nicely the curve that we create adapts to the control polygon. And now here I'm going to double click and I'm going to create a point container. And this point, I'm just going to right click and I'm going to set multiple points. I'm going to set this one, and remember that the order in which we set them is important. You can see that I can see the order because Rhino is already giving me this kind of control polygon. I'm going to drop some bifocals bifocals, so that those who are not used to icons can still see the names of the components. And I'm just, for the sake of visualization, I'm just going to create a polyline between these points. This is just for visual flavor, but we don't really need that polyline at all. And to create a C# script component, I'm going to double click, create C#. I'm going to rename the inputs. For example, right click. I'm going to type here PTS, as in points. And here I'm going to, for example, iterations. So how many times do we want to iterate over this curve? And I'm going to right click on PTS. I'm going to make sure that this has list access, so that instead of reading one point at a time, I can read them as a list. So that's one thing. The other thing is that I want to make sure that the type is point 3Ds. Similarly, for iterations, I want to make sure that it's on item axis, so I just want one number, and that the type of the input is going to be of the type double, because I want numbers to be here. Actually, you know what? That's not right. I don't want doubles. I want integers, because I cannot do 1.3 iterations. So that has to be an integer. And then here, I'm just going to drop a slider connected to iterations, and so that I can control whether if it's 1, 2, 3, 4 iterations, whatever. And then right here inside, now I have my my C# scripting component ready, which at the end of the day is just this one function that Grasshopper gives us that contains a list of point3D objects, and this is a list because I clicked on list access, and an integer, which is the number of iterations, with the result being a referenced object, which I'm going to I'm going to say, for example, I'm going to call this I'm going to call these points out, for example. And if I double click here, you can see that the reference is now points out. All right. And given this, I am now ready to start writing some code and making this happen. I think the first thing that I'm going to do is I'm going to bring in the function that calculates a point at a relative distance between two other points. And we implemented that in a previous geometry gem, which you can probably find somewhere on the links. So let me go and find that and bring it back here. Right, so I went back through my videos and I went back to geometry gem number 6, in which we discussed how to find a point at a relative length. So I did copy the function that I created there, which is called point along line. A and B and T is the relative distance along that line. I'm going to just write here from geometry gem number 6, okay? Which, as I'm recording this video right now, still is not published, but it will be published very soon, okay? So if you wanted to know how this works, just make sure that you go to the geometry gem, all right? And now here, we are ready now to implement the algorithm to do recursively to find many of these points. So let's take a look at how would we do that. So the process for the computational algorithm is going to be also super simple. Let's imagine we have a list of points, okay? A list of points that is going to be, these are going to be the control points. What we're going to do is we're going to create some kind of function or operation that we're going to call smoothing, for example. So we're going to smooth these points, and as a result, what we're going to get is another list of points, which are going to be all these points here in the middle. This one, this one, this one, this one. So we started with the original control points, so these ones, and as a result of smoothing, we end up with this list here, which is this point, this point, this point, all of these points here, right? And again, remember that we don't really care about polylines. What we care is about an ordered list of points, which is the same thing as a polyline at the end of the day. And then once we have this, we can just repeat this process as many times as we want. So we can just take these points and make them those original starting points that we then smooth again, over and over again. And how many times we do this, this is going to be defined by our iterations. And I didn't know how to write that. That was a terrible diagram. So we're just going to have a list of points that we're going to keep mutating and subdividing and smoothing according to this particular rule that we have devised. Okay, so let's see how that would work code-wise. Okay, so let's start by doing one iteration of this process, and then we implement how a full set of iterations would work. So let's start by creating that list that we're going to be working over and over again. So create our working list of points, and I'm going to call that, for example, that's going to be a list of point 3D objects that I'm going to call control points, for example, and that's going to be a new list of points, which I'm going to control points is like a new list of points 3D objects, and something that is usually good practice is, instead of working directly with the input of the function, working with a copy of the list that is coming from the function. In Grasshopper, that doesn't really matter much, because at the end of the day, everything is copies. But if you're working in a different environment, you probably don't want to mess with the original list that you got. So it's probably usually good practice to copy as a clone or as a copy. And we can do that by creating the new list of point 3D objects, and here in parentheses, passing in a list that we want to copy. And because these objects are structs, they're not classes, we're probably going to end up with a copy of this list. Okay? Then what we may want to do, and this is just one iteration, what we may want to do is something like saying, I'm going to create another list that I'm going to call smooth points, and this is going to be the result of some kind of smoothing operation. So for example, smooth polyline, which I haven't implemented yet. I'm just like designing the algorithm. And this is going to take as an input these control points. And it's also going to take as an input the smoothing value. We discussed how this is a quarter, right? And then after that, we say the output is going to be points out, for example, which is going to be these smoothed points. Not pots, but points. All right. And obviously, if I run this, it's not going to work because there's no smooth polyline function at all. So the name smooth polyline doesn't exist. So I'm going to go here all the way down to custom additional code. This is where in C# script components, this is where you add your functions. So this is the global scope of sorts. And here I'm going to create that function. And the input, as we said, is going to be a list of point 3D objects that I'm going to call points, for example. The fact that this is called PTS has nothing to do with this. It's independent. And then a double value, which is going to be, for example, T. And that is going to be where, along those lines, those control points are going to be found. All right? And then we need to remember that we also have to implement here the return type of this function, which is going to be another list of points. So it's given a list of points and it returns another list of points. So it takes, going back to the diagram, it takes the original control points, all right? And then it returns a new list of control points, which are the ones in the middle, these ones here. Oh, so much stuff. So now I'm going to add some code here. Returns a list of smoothed. Is smoothed a good English word? I'm not. I don't know. Of smooth control points for the polyline. All right. And then here it's going to be very easy. What we're going to do is we're going to create a for loop where we're going to go over each pair of points, this one, this one, this one, and we're going to find the two control points that we need in between those two lines, in between those 2 points, and we're going to add them to a list, an empty list that we're going to keep populating with these points. So how does that work? Let me create a list of points, 3D objects. For example, new points. And this is going to be a new empty list that we're going to initialize here. Empty list to populate with new points. And now we're going to write a for loop to go over all the original control points. So this one, this one, this one, this one, this one. So this for loop, I'm not going to start it at 0. I'm going to start at 1 so that for each point, for this one, for this one, for this one, what I do is I look at that point and the previous one, and then I calculate the points in between. So I'm going to say for a for loop that starts at 1, and that is where I is less than the length of points and I increases 1 by 1. All right. What I'm going to do is for each pair, I'm going to take for each pair, I'm going to say the first point is going to be point A, and the second one is going to be point B. When I do the second segment, this is going to be A, and this is going to be B. For the third segment, this is going to be A, and this is going to be B. How is that? I'm going to create a point 3D object called A, and that's going to be, in points, is going to be the point that is at location I minus 1. All right, and point 3D B is going to be from the points is going to be the one that is at location I, because remember, I started counting the for loop. If this is point 0, I started with point 1, point 2, point 3, and point 4. So I want to take that point and the previous one. So that is point A and point B. All right? So as I do that, I can say, let me calculate the point D. I'm going to call that, what am I going to call that? B0 is going to be a point along this line between A and B, which lies at 0.25, right? And then point 3D, P1, is going to be a point that lies along that line at 0.75. As we have those points already, now to the list that I have created, I can add P0. And to the new points list, I can add P1. And this for loop will take care of going through all those points and calculating the 2 points in between each pair of points. So as we finish this for loop, this list here should already have 2 points per segment of the polyline. So now I can just return new points, and this should work. So is that going to work? Let me say, oh, no errors. And what if I plug a panel here? I have a list of points, and you can also see that these points here, I have a collection of points that are at point 25, 75, point 25, 75, etc., along each one of these. And if I move the polylines, you can see that things adapt nice and smooth. All right, and very importantly, for these control points, I do not have this point, this point, this point. Those are not in this bucket here. So this is working well, and I have been able to do one iteration of this, but I skipped through some things, so the code is not very tight, and also we don't have like a full iteration. So let's do a couple fixes there. You might have noticed that here I just hard-coded 0.25 and 0.75. But this is not great design because the input of the function allowed me to customize that parameter. Here I'm calling it with 0.25, but I want these two values to be linked to that length, that relative length that I want to calculate. So how can I do that? Very easy. So I can just compute the relative lengths of the points. So that's going to be, for example, I'm going to call the first one T0, and that's going to be equal to T. And so just that value. And then T1 is going to be equal to 1 minus T. So if this is 0.25, 1 minus 0.25 is 0.75. So now I can substitute here T0, and I can substitute here T1. This is going to give me the same result. But what's nice about this is that now this allows me to play a little bit with that parameter as an input. So for example, here I can say, for example, T, or not, I'm using this too much. I'm going to call this proportion, for example. That's a terrible name. But if I write a slider here and I plug it in here, I make sure that this is of the type double, and then I replace this hard-coded number. I really don't like hard-coded numbers in algorithms. So, and we replace this with prop, okay? Now I got the same result. Everything is working well, but you can see that I can now customize where those points are along my line, and I can even flip them, you know? Whether if this will be interesting or not for the curve, I don't know, but this is the kind of things that I like doing when I'm doing computational design. I like to challenge values, and I like to challenge numbers and see where I get with them. Let's keep in mind though that the original algorithm says that this has to be a quarter of the length of the line. This has to be 0.25 to be the original Chaikin's algorithm. And it has to be like that in order to generate quadratic B-splines between the control points. Otherwise, it's not the original algorithm, it's our own interpretation of the algorithm. This is very important to notice, okay? All right, so I think at this point, we are ready to now change the code a little bit and implement iterations of this. Let's take a look at that. Right, so going back to the diagram that we showed before, what we're going to do now is just, in order to perform several iterations of this process, what we're going to do is we're going to take the original list that contains the points, we're going to smooth it, but then we're going to overwrite that list over and over again, how many times, however many iterations we want to implement out of this. So that's going to be super simple. I'm just going to go here. Oh, and I forgot before, something very cool that we can do is we can just join all these points with a polyline so that we can see how the polyline is actually smoothing, right? So I'm going to double click here, and you can see that just to get things out fast, what I did here was I created a new list, all right? But something that I could have done is I could have just taken the same list and overwrite it with the result of the smooth polyline, and that make it the output, all right? Because remember, when you write code, very often, like 90% of the languages that I know of probably, statements are executed from right to left. So this gets executed first with whichever value for the points was coming here, and the result of that then gets assigned here, so it gets overwritten. So we can do this one time, or we can just wrap this in a for loop where we say, I'm going to create a for loop that starts at 0, where I is less than the number of iterations that we want to compute, and I++, and then we don't really need that I for anything. This is just a matter of controlling how many iterations we execute. So iterations of smoothing. And then once the result is done, then we just output that result. Let's see, are you guys excited? Is this going to work? Boom! Oh my god, we got something here. So we had 2 iterations, and you can see how the curve smooths from 1 iteration, 0 iteration, so that's the original, 1, 2, 3, 4, 5, 6, 7, 8. And you can see, if I turn off the control points, you can see that this curve, to me, this polyline, to me, looks like a smooth curve. My eye cannot really distinguish the tiny segments that are making this polyline at all. What is the limit? You see, I cannot see the difference between 8 iterations, 6, 7, 6, 5, 4. I can see now some, yeah. So 4, I don't like 4. 5 is already pretty smooth, but I think 6 is so many points that I can barely tell them apart. And so, yep. So this is basically Chaikin's algorithm. And something that is very nice about this algorithm is that it works in 3D as well. So the points that we chose were all on the plane. But if I move this point up in space, you can see that the logic of the algorithm still stands, and that the curve still works in 3-dimensional space. So this is also something very nice. It's very effective, and as you have seen, the code is like very, very simple to implement. It's very nice and very elegant. Let's take a little bit of time also to indulge in what we've done. I'm going to go back to 2D, and let's explore the idea of where those points lay on the control point. Because remember, the original algorithm says that the control points must be a quarter of the ends. But if we play with this, so if we make this value smaller, you can see that we have this effect where the curve is actually snapping closer to the original control points, the original control polygon, and it's doing some weird curvature here that is not very nice. But if I smooth it out a lot, for example, if I bring it closer to 0.35, 35, 40. We also see that, yeah, it's more detached, but we also see these kind of kinks. So it's also, that's not very great. And if we push it farther, what is this? This is so cool. This is not a smooth curvature at all, but if we flip the points and we move them past, so the point that was here now is first and then the second, we create this sort of like fractal curve or of some kind. It's kind of like an inverted like Chaikin's algorithm curve. This is really, really cool. What is happening there? What? What is this? This is really interesting. Huh. Okay, I like this. And if we take it all the way to 1, we end up with this strange triangulation. Huh. That's very cool. From control polygon to smooth to fractal to triangles. Huh. This is very nice. All right. So, long story short, or bottom line, algorithms are nice to follow by the rule, but keep in mind that I like being a designer, so I like challenging rules. And a rule that is driven by one number is definitely something that I would like to explore. What happens if I change that number? I'm getting a suggestion on the chat to give it 0.75. That's a really nice result as well. What if yeah, let me bring this back to 3D and see how those curves change, that geometry changes spatially. Huh, nice. It kind of feels like it sticks to the plane. And what if I give it 1? I get that, I get this like really interesting triangulation, huh? I wonder if this could be something that we could use to go from a polyline to a mesh with triangles. This could be an interesting thing to explore. Cool. All right. So going back to 0.5. All right. So this is the original algorithm, and I'm going to bring this planar. And I probably want to spend some time trying to implement also whether if this curve is going to be closed on itself or it's just going to be open. Whether if we want to make this curve periodic or not. So how about we give that a try? The notion of how to make this curve that we're going to generate closed or how to make it periodic, which is the technical term usually referred to for closed curves, is actually going to be very easy. So if imagine like a simple control polygon like the one we have 4 points and we have this polyline that goes around them. If we draw that curve, the curve that our algorithm will generate will be something like this. And remember that it doesn't really reach the first point or the last point because we start taking like a fourth and a fourth and a fourth away, you know? So, but if you think about these points being the 4 points that we created and being 0, 1, 2, and 3, if what we want is to make this curve continue and start closing into itself, then a very simple technique to do that is just to work with a list where we extend the control polygon to loop over into itself. And to do that, it's just as easy as adding to the same list, duplicating this point on top of itself at the end of the line, so that if we created a polyline, the polyline would look something like this. So it would have like the last segment would be coming all the way here, right? So that feels like that should work, but it's not going to work entirely because if you remember the algorithm will probably end up doing something like this. It will extend beyond the last point into this segment, but it will also stop here because remember, we take like the end, we take like a fourth of the end of the extremes away. So what we need to do for this particular algorithms is we actually need to duplicate this point again all the way at the end of the list, making it the 6th point, or the one with index number 5, so that our polyline is something like this. It's 1, 2, 3, 4, and 5 segments, and so that the curve ends up wrapping on top of itself and ending up very nicely here at the beginning of the point of the curve. So that is very, very simple to implement. So what I'm going to do here, I'm going to add a new input. I'm going to call this periodic. I'm going to make sure that this is of the type Boolean. And then I'm just going to drop here a Boolean toggle. Okay? The Boolean toggle that I'm going to set to true, and then I'm going to place here so that I can control if I want this closed or not. I'm going to double click here, and here in the operations, when we create our list of points, the list of points is just 1, 2, 3, 4, 5, and 6. But if we want to close, or we want to make this curve periodic, what we can do is we can say, let's check if the user is setting it periodic, if the input, there's an input called periodic. So if this is true, or a shorthand for this is just to say if periodic, so that works exactly the same. I'm going to write here duplicate points for a periodic curve. All right. And if that's true, the only thing that I need to do is to my list of points, after the last point, I need to add a copy of the first point. So what I can do is I can say for control points, let me add at the end of that list a copy of the first point that is currently on that list. If I do that, you're going to see how immediately as I press play, the curve starts wrapping on top of itself, because there is now this one line segment here going here. But as I explained before, it's not going to close up nicely with this one, because we actually need to duplicate also the first point. So the second point on the original list. So when I do this and I press play, now you can see that it goes all the way and it wraps up very nicely all the way here. And obviously I can modify these points and I can move them around in 3D space, and the curve adapts very smoothly to the whole operation. Okay, one thing that came up and while we were recording this video and Arasto on the chat helped me find this bug, is the fact that the algorithm is actually the output points. There is one point that is duplicate and is creating like one segment of the polyline at the very end, overlapping the first segment. So if you see here, the first point and the second point are duplicate on the list, which means there is one segment of the polyline that is overlapping on top of itself. And this happens no matter how many iterations you create. There's always the first 2 points are duplicate at the end, which it doesn't really affect the visual result, but we know that here there's this segment of the polyline is duplicate, and it's not a clean solution. All right, it's not a clean algorithm, and we like clean algorithms. We're very rigorous and parametric people, so why not fix that? So I'm not really sure why that's happening, but a really quick fix is just to remove the very last point of the list before outputting the polyline. So that's very easy to do. We can just go here and say, let's remove the last duplicate point from the list of points. After doing all the iterations, just remove the one that is at the very end of that list. And if we do that, you can see that now we do have the first point is duplicate, and that's what we want because we want the polyline to end on the first point, but we don't have that additional point creating the one segment overlap on the polyline. So the algorithm is a bit cleaner now, and thanks a lot, Arasto, for catching that, okay? Oh yeah, and a quick thing, this only happens if the curve is periodic. So if periodic, then that's when we remove the last point, not in every case, okay? And I think that's it. So again, we can play with the triangulation with the parameters. We can play with whether if it's periodic or not periodic. But this is a very, very simple polyline smoothing algorithm that comes from a very simple rule. And as I said, one of the nice things about this is that each one, so this by definition is a piecewise quadratic B-spline, which means that the curve that is going from this point to the center of this point is a quadratic B-spline. The curve that is going from this one to this one is also a quadratic B-spline, from this one to this one, etc., etc. And also, if I close them up, this segment and this segment. And I think that's it for me today. I hope you enjoyed the video. I hope you learned something. I hope you had fun playing with the parameters. And if you like what you saw, it would be nice if you like the video, if you subscribe, turn on notifications, and all those things YouTubers do these days. Thank you very much, and see you in the next gem.